Hello and welcome back. So far we've talked about single outcomes and the probabilities, and now we want to move from single elements to sets, and we'll call them events. And we'll talk about what it means for an event to occur and what is the probability of an event, and then we'll calculate the probability of events when the sample space is uniform. Right, so let's start. We all know that when you're single, outcomes a life that not that interesting. So what to do? Well, we're just going to have to make our life more eventful. Okay. So what are events? So sometimes we're interested in one particular outcome. For example, that our horse will win a race, or that we'll get exactly a B+ in class. But usually we are more interested in a set of possible outcomes, in a collection of possible things that could happen. For example, that the temperature is going to be above freezing, or that our stock will go up in price, or that we'll pass the course. In all these cases, we're interested in a set of outcomes, or in other words, a subset of the sample space omega, and we call those events. So why do we call them events? Well, a social event is a collection of people, a set of people, and similarly, a probabilistic event is a set of possible outcome, or in other words, a subset of the sample space omega. Okay. So let's look at some events on a die. So event, as we just said, is a subset of the sample space omega, and for a die, the sample space is the collection of all integers from 1 up to 6, and therefore any event is going to be a subset of that set. And so let's look at a couple of events. The event consisting, which is the set consisting of all the integers from 1 up to 6, well, that's omega itself, which we'll also call the certain event. The event or set consisting of the outcomes 2, 4, and 6. For simplicity, we can call it just the even event. The event or set consisting of 1 and 4 we'll call square, because we have squares, in every element is a square. The event consisting of 5 and 6 we'll call either bigger than 4 or bigger than or equal to 5. And sometimes we'll get an event like 1 to 5. We cannot find a cute name for it, so we'll just keep it as it is. It's the event 1 to 5. And whenever you have an event which is a set, you can look at complements of sets. So the complement of the certain event is the empty event, which we'll call the null event, and denoted by empty set. The complement of the even event is the event consisting of 1, 3, and 5, which we'll call the odd event. The complement of the square event is 2, 3, 5, and 6, the elements not in 1 and 4, which we'll call the non-square event. And likewise, the complement 5, 6 is 1, 2, 3, 4, which is the event less than or equal to 4, or bigger than or strictly less than 5. And the complement of 1 to 5 is just 3, 4, 6. Okay. Now, if we look at the tetrahedral die, which, if you recall, the faces are 1, 2, 3, and 4, probabilities are 0.1 and so on, then the omega or certain event now is 1, 2, 3, 4. The even event here is just 2 and 4. The prime event is 2 or 3, not 1 and not 4. And the null event is just the empty set. Okay, so now that we know that events are just simple subsets of omega, let's see when we said that an event has occurred. So we said that an event occurs if it contains the observed outcome. In other words, E occurs if the random outcome X belongs to E, belongs to the set that E represents. Okay, so in the case of the tetrahedral die, 1, 2, 3, 4, let's see, we'll talk about the events, the subset they correspond to, and the outcome. And what we'll do is when event occurs, we'll write a check mark. When it doesn't occur, we'll put an X. So if we have the certain event omega, the subset is 1, 2, 3, 4, all the possible outcomes of the die, this die. So if 1 occurs, then the event occurs. If 2 occurs, it belongs to the set. So it occurred. If 3 occurred, again, it belongs to the set, so the event occurred. and if 4 occurred, again it occurred. So in other words, the certain event omega always occurs. Let's look at the even event 2 and 4. Well, if the outcome is 1, then it's not in the set, so the even event did not occur. If the outcome is 2, then it's in the set, so the even event occurred. If the outcome is 3, then this even event did not occur. If the outcome is 4, the even event did occur because it's in the set. In other words, the even event occurs if we get 2 or 4. If we look at prime, the sets are 2 and 3, and you can see that this event occurs if we get 2 or 3, and this event will not occur if we get 1 or 4. And if we look at the empty or null event, which consists of just the empty set, then this event will never occur because we'll never get an outcome that is in the empty set. Right. So now that we know what it means for an event to occur, we'll talk about event probability. So the probability of an event E, which we'll denote by P of E, is just the probability that the event occurs, namely that the outcome belongs to the event. The probability that the random outcome X belongs to this event E. Okay. And as before, we're going to define it to be the fraction of experiments where it occurs as the number of experiments grows. Okay, so here is the tetrahedral die. And then the even event, let's say we want to calculate the probability of the even event, P of E, where E is the even event. Then, and we're going to do it as a fraction of times that the even event occurs. So let's say we take an experiment that consists of rolling this die 12 times, and let's say that the outcomes are like these, and then we can see which outcomes were even, and here we have that 4, 2, 4, and so on even, and the number of even outcomes that we got out of the 12, 7 of them are even, and therefore we can estimate the probability of even to be roughly the fraction. The reason it's roughly is because this number of trials is 12, is not infinite, so it's approximately the probability of even. In this experiment, it's 7 over 12, number of times the fraction of time that this event occurred, 7 over 12, which is total number of times, which is roughly 0.583. Okay? So now what we really want is to find the real probability of E, which is the fraction, but not for 12, but rather as the number of experiments goes from 12 to infinity. So that's number 1. And number 2, we want to do it not just for the even event, but we want to do it for general distributions and events. Okay. So what we want to do, therefore, is we want to relate the probability of an event to the probability of its elements, or the probability of possible outcomes. Okay. So taking our green die again, the number of times that the even event, for example, occurs is the sum of the number of times that 2 occurs and 4 occurs. That's the total number of times that this event will occur. And therefore, the probability of even, which is going to be the fraction of time that the even occurs, is just going to be the fraction of times that 2 occurs plus the fraction of times that P occurs. But the fraction of time that 2 occurs is the probability of 2, and the fraction of time that 4 occurs is the probability of 4. So the sum is just going to be P of 2 plus P of 4. So in other words, for the even event, the probability of even is going to be the probability of 2 plus the probability of 4. Similarly, for a general event E, the number of times that E will occur will be the sum of the number of times that its elements will occur, just like we had it here. Okay, and therefore the probability of the general event is going to be, as we define the fraction of times that this event occur, E, and this is going to be the sum of the fraction of times that its elements occur, and each element, the fraction of time that each element occur is the probability of this element, so it's a sum of its elements or element probabilities, and therefore we get that the probability of an event E, which is the probability that X, the random outcomes, belong to E, is just the summation of the probability of each element in E. Right. So let's look at the tetrahedral die again. So remember the probability of the elements are 0.1 up to 0.4, and we want to use that to find the probability of different events. So if we have the certain event, the set is 1, 2, 3, 4, and this event occurs if all the elements, any of the elements occur, and the probability of the event is just the sum of the probabilities, which is 0.1 plus 0.2 plus 0.3 plus 0.4. The even event consists of 2 and 4, and the probability of the event is just 0.2, the probability of 2 plus the probability of 4, which is 0.6. The probability of a prime event is the probability of 2 or 3, which is going to be P of 2 plus P of 3, which is 0.2 plus 0.3, which is 0.5. And the probability of the null event is just the sum of no elements, which is going to be 0. So we say that the probability of the null event is 0, that's always going to be the case, and the probability of the certain event is 1, and that's always going to be the case. Okay. Now, we can specifically look at uniform spaces, which as we recall, we also called equiprobable spaces. And for these spaces, we had a simple formula for the probability of outcome, right? It was just 1 over probability of any outcome x was the same, it's 1 over the size of the space. And the question is whether we can have a simple formula for the probability of an event. And the answer is yes, because the probability of event in an equiprobable space is, as we saw, is just the summation of all element probabilities, all elements in E, in the event. And because we're talking about a uniform space, then each probability, the probability of every element is 1 over omega. So we're summing over all elements in E of 1 over omega. So we can take 1 over omega outside, and we'll get it's 1 over omega times the summation of all elements in E of 1. And this numerator is just the size of E divided by the size of omega. Okay. So for the die, for example, omega is 1 to 3 up to 6. The size of omega is 6, and we have a uniform, and it's a uniform space because every element has the same probability. So if we look at the event and the probabilities, so the even event consists of 2, 4, 6. The size of this event is 3. The probability of this event, or the even event, is going to be 3 over 6, which is 1/2. Okay, so that's a probability that x is 2, 4, or 6. The square event consists of 1 and 4. The size of this event is 2. And the probability of the event is therefore going to be the size of the event divided by 6, which is 2 over 6, which is 1/3. Okay. And finally, I just want to mention a little bit of terminology. If A and B are events, then they can intersect or they can be disjoint. If they are disjoint as sets, we call them mutually exclusive. Right? So as we did with outcomes, single elements, I want to just say what we cannot say, or which expressions are valid and invalid for events. And so let's list a few of those. So how about the probability that x belongs to even, and here x is capital. Is this a valid expression or not? How about just writing the probability of even? Or the probability that 3 belongs to even? Or the probability that 4 belongs to even? Or the probability that x belongs to even, and here x is small x. So which of those are valid and which are not? So the first two are all right. For example, the probability that x, the random variable x, belongs to even is, if we have a die, for example, is the probability that x belongs to the set 2, 4, 6. And that's, in this particular case, it's 3 over 6, which is 1/2. How about the probability of even? Is that a valid expression? It is, because this is just our abbreviation for what we have above, the probability that x belongs to even. How about the next two? Well, these are a little more iffy, okay, but there is an interpretation under which they're correct. So 3, we can view it as a special kind of random variable, constant random variable. It's always 3, okay? So therefore, it's possible to write it. It's just a special case of what we had before. And notice that this quote-unquote random variable, the constant random variable 3, is never in even, because 3 is odd. And so the probability that 3 belongs to even is 0. And similarly, the probability that 4 belongs to even, now we can look at 4 as the random variable that's always 4, that probability is 1. Okay. So this, however, typically you will not see this that often. So if you write something, just make sure that this is what you meant to write. How about writing the probability of small x belongs to even? Well, that's even less likely. Because what is x here? So this is like what we had in the previous two lines, but even worse, because it's not clear what x is. Okay, so you need to clarify here what x is. For example, you can write it for all x in 3 and 7. So for 3 and 7, the probability that x is in even, you can say that, and that probability is 0, because the probability that 3 belongs to even is 0, and probability 7 belongs to even is 0. So this expression you can write, if you write this expression, it's okay. So it make even more sure that this is what you meant to write. Okay, so with that, we've talked about events and their probabilities. We said that we're moving from single outcomes, which we've done before, to sets of outcomes. And we said that an event is a subset of the sample space omega. And we said that an event occurs if the outcome that we observe is in the event. And we talked about the probability of an event, and we said that it's the probability of E is just a summation of the probabilities of all the elements in the event. And what are we going to do next? We're going to look at repeated experiments. See you then.